And we really did here just what we did in the Cartesian example that you did for homework, the Cartesian problem. And then you should have written out the complete set of solutions, right? Or rather, a sum of the complete set of functional solutions. And then you apply the boundary conditions, and that begins to limit what the possible functional solutions are, right? So what we did here was we wrote out that horrible mess, which was the complete set of solutions. Then we inspected our problem, our situation, in which I had applied a field, and I claimed this. Here's where the physics comes in. This may be the only place where the physics, two places where the physics comes in. One is that the perturbation to the field must disappear when you get far enough away from the cylinder. All right, and oh yeah, don't forget this was a cylinder, and that's why the perturbation to the field dropped off as 1 over r squared. You might have thought of this, and you would find, we will find, if this were a spherical particle, metal, placed in a constant electric field, the perturbation to the field will fall off as 1 over r cubed. All right? But because this is a two-dimensional problem only, because this is an infinite cylinder, the perturbation to the field drops off as 1 over r squared. So we did this right. The physics came in when we said far away, we have to reduce to the field that we had without the rod in there. So that's good, all right? And that the potential on the surface is constant. That was it. Those were the only elements of physics. All the rest of it was actually a math problem that you have probably solved in another course. Did you solve this in another course? No. Okay, good. It's a math problem you could solve having taken another course. And what course would that be, actually? Differential equations?
Yeah.
Mm.
We did something like, we did things like
Okay.
that, not this question problem.
So here's a problem I'm not going to solve for you, and I won't give it for homework. And it's not in the textbook. It's not a problem. It's a situation, let's say.
Is it
What would we do?
Is it a
What would you
problematic
do?
situation?
Not me. I wouldn't do it. What would you do if this cylinder here were finite? What? What's your answer? Go away. Well, what if you wanted to get an A in the class and I gave you this problem?
Computer.
No. It's not that bad.
Wolfram
It's not
Alpha.
that bad.
But
So you assume I actually wrote the correct Laplacian, and I showed it to you. Okay, the Laplacian is the Laplacian for cylindrical coordinates. I'm just cheating here. Plus d squared by dz squared is equal to 0.
Z squared.
Z squared.
Don't you mean Laplacian for polar? Because that's part of the Laplacian for cylindrical?
Polar. There we go. Okay. Yeah, you have to do that since Brian's not here.
I have to fill in for him.
Yeah. I am not saying something. Yeah. So, oops. Yeah, that's what it looks like. We can separate variables, and we do separate variables. And first, typically we separate the phi solution, and we do find that q of phi is sine n phi or cosine n phi. And of course, I should write that out as a sum, a complete sum of solutions. Right? But sum of a complete set of solutions, but I'm not doing that right here. Okay? Then, having separated out the phi solution, we have to separate out the z solution. It's not so easy anymore. And so separating out z is easy. And I think that I chose, in this case, to make the z functions sines and cosines as well, right? So I had for my z, 1 over z, d squared z, dz squared is equal to, in this case, I raise a constant squared, right? So now I've taken care of the z, but what that does is it really messes up the solution in rho. So I get 1 over rho, or d by d rho, rho, r, rho, plus n squared coming from the q solution, right, over rho squared, plus gamma squared is equal to 0. Right? So my differential equation in radius, in rho, has got this extra term in here. Right? That extra term's okay, it doesn't bother us at all, because we can just look in Chows and discover that there's a whole set of functions that are the solutions to that problem. Yeah, I'll do. I'm always deciding how much of it I'm going to show you. This is a good place. Then a miracle occurs. And if I use some f, it's not a function, equals gamma, the gamma that I owe over there, times rho. So I'm just changing variables, right? Then that equation becomes 1 over f, oops, 1 over f, d by df, f, dr, f. That. Does anyone recognize that equation?
Yes.
Do you know its name? The ball?
It looks like the one.
This is called Bessel's equation. And I'd be surprised, for those of you who took optics, if Professor Schroeder didn't actually go in detail through the solution of this. Did he? Nope. It's supposed to be a sophomore level course.
Well, I mean,
Okay? The solutions to that equation are Bessel functions.
Wow.
Which are really just series. What you actually do to find out what the Bessel functions are, what Bessel did, was assume that the solution was a polynomial series. And then he figured out what the coefficients on the polynomial series had to be in order to satisfy that equation. Right? So in your differential equations course, they're actually going to do that. They're going to, I hope, assume that the solution is in the form of a polynomial series, and then plug stuff in and figure out what conditions have to apply to the coefficients on the polynomial series. All right? No? Didn't do that? Okay.
sort of.
Bessel functions are just polynomial series. But they look and by the way, you could do exactly the same thing with sine and cosine functions in finding the solutions to the simpler differential equation that we had up there. And we just say it's sine and cosine. But you could assume that the solution is a series solution polynomial series solution. And then you find out that the terms in the polynomial series are something like plus 1 over x minus 1 over x cubed times some factor, probably 1 over 3 factorial or something like that. And by the time you're done, you've discovered that you've written down a sine function. Right? So that's all that this really is. You know, if you had to solve this without recourse to tables or shams, you'd assume a series solution and find out what the coefficients are. Take you a couple weeks to do it right. Those are n's. So I've got an n in this equation, and that's it. This is a function of this sort of radial variable, scaled radial variable. And Bessel functions actually look sort of like sine functions and cosine functions, but they decay. So a Bessel function for, actually I think it is actually J1. Looks like that. It actually decays approximately as 1 over rho, or 1 over f, right, over there, but 1 over rho distance. And that means that because I have something finite, I have my cylinder is finite, when I get really far away, the potential is going to drop off with an extra factor of 1 over rho, because that's what the Bessel function is doing when you get far away. Okay? So making something finite actually in the end gives you the correct asymptotic behavior. The Bessel function introduces that asymptotic behavior. Okay, I think I'm going to stop for 10 minutes now, and then go to spherical coordinates.